strength of a relationship, of a numeric relationship. So correlation has this very specific meaning in statistics, okay? And I know in day-to-day language, well, I don't know how often you use the term correlation, but correlation, you might say two things are correlated just to say that there's some kind of relationship between two things, okay? And I guess in day-to-day conversation, it's acceptable to say, you know, these things are correlated, you know. Someone, you know, political preference is correlated to, you might say, like, political preference is correlated with race or something like that, okay? Technically, and from a statistical standpoint, it would be wrong to say that because both race and political preference or political party are categorical variables, okay? But if, so correlation only applies when we're talking about numeric variables, but in day-to-day language and speech, we say things like that, or maybe I wouldn't say that, but some people might say things like that. But in statistics, correlation, or to say things are correlated, we need to be talking about numeric variables. Okay. I would probably use the word is related to or seems to be associated with to avoid using the word correlation. But that's just because well, words mean different things to different people, so. Okay, so let's talk about calculating correlation, okay? So correlation can be thought of as the sum product of z-scores, quote, the quote average sum product of z-scores, okay? This is a terrible, loose definition, okay? It can be thought of as the average-ish, I guess, product of z-scores. Okay, so let's think about what that means. A z-score is what? What is a z-score? Z-score is how many standard deviations we are from the mean. Right? Okay. How many standard deviations we are from the mean. So, in a set of data, we would look at each data point, and we would say this data point is high above the mean in x and high above the mean in y. And we would multiply those z-scores together. Whereas another data point might be low, might have a high negative z-score in x and negative z-score in y. Okay? I'm going to so we'll try something out. Okay, so R can be thought of as you take the z-score for x and the z-score for y, and you multiply those two together, and you add those up, okay? And then after you add them all up, you divide by n minus 1. I like to use n minus 1. So that's why I say quote average. If we expand what each z-score is, we can think of R as some product of x minus x bar minus y bar over the standard deviation of y. Maybe I'll put these in parentheses. I'm going to just further expand this, or not expand, but I'm going to simplify this sort of. So this is the sum of this product here, okay? For every data point that we have, the x is different and the y is different, okay? But the standard deviation of x is the same for every single data point, and the standard deviation of y is also the same for every single data point. Okay? So I can factor out the standard deviation of x and the standard deviation of y. So I'm going to have 1 over n minus 1 times 1 over the standard deviation of x times 1 over the standard deviation of y multiplied by x minus x bar times y minus y bar. So this would be a way for us to calculate the correlation. Correlation coefficient. So we'll try this out for a very simple example here. So let's say this is our data. Okay, this is not a great example, but it will work. Okay, let's say we want to know, is there a relationship between the number of bedrooms in a dwelling and how many closets this dwelling has. Okay? And so we'll say bedrooms will be x and closets will be y. And I'm picking these points, but okay, so let's say we go to a one-bedroom place and it has 2 closets. Okay? And then we go to a 2-bedroom place and for whatever reason it has 6 closets. We go to a 3-bedroom place and it has 4 closets, and we go to a 4-bedroom place and it has 8 closets. Alright, so let's say this is what we have, and we want to know what is the correlation between the number of bedrooms in a place and how many closets this place has. I'm going to create a scatter plot. So this is what my scatter plot looks like. 1, 2, 3, 4, 5, 6, 7, 8. This would be closets and bedrooms. Okay. So what is the correlation between the number of bedrooms and the closets? Okay, so to calculate correlation, we're going to find the mean. Okay, so x bar, in my data set of 4 places that I visited, what's the average number of bedrooms that I see? Well, I would do 1 plus 2 plus 3 plus 4 divided by 4, and I'll get x bar is equal to 2.5. And as far as closets go, y bar, the average of these four numbers, is 5. Do we remember how to calculate the standard deviation of a set of numbers? Kind of. Okay. So the standard deviation for did y minus y bar squared summed up divided by n minus 1 squared. Okay, so we would do that for each set of 4. Okay. 0.5 squared plus so I get 1.291. And over here I get 2.582. So that's all I've done. I have a set of 4 numbers, and I take its mean and I take its standard deviation. I have a set of 4 numbers, take its mean and I take its standard deviation. And now we are going to look at basically how far it is from the mean, x minus x bar, and y minus y bar, and we will look at the product of those two values. Okay, because we're going for x minus x bar times y minus y bar. So another way to think of this is I'm going to draw dotted lines at 5 and at 2.5. And so this data point right here is 1.5 units away from the mean. Okay, so I do 1 minus 2.5, I get negative 1.5. And if I look in the y direction, I get 2 minus 5, I get negative 3. Okay, so we are this far away. This data point, 2.6, is over there. So it is below the mean of x, but it's above the mean of y. So I have positive 1. And over here I have 3 minus 2.5, and I get positive 0.5. 4 minus 5, I get negative 1. And over here I get positive 1.5. 4 minus 2.5 is positive 1.5. 8 minus 5, I get positive 3. I multiply these together and I get negative times negative gives me a positive 4.5. This times this gives me negative 0.5. These two multiplied together gives me negative 0.5. And these two together gives me positive 4.5. So if I add all of these up, this adds up to 8. So the sum of x minus x bar times y minus y bar is equal to 8. And so correlation is equal to 1 over n minus 1 times 1 over s of x times 1 over s of y times that thing. Okay, so I would have n minus 1 is the number of pairs of points that I have. So n is 4. So I would have 1 over 3 times 1 over 1.291 times 1 over 2.585 582 times 8. And when I do that, I get 0.8. Pretty sure. Yes?
What was the product column? How did you get that?
This is, this times this is equal to this.
Oh.
Okay, so negative 1.5 times negative 3 is positive 4.5. And I do that for all 4 data points. So for the 4 dwellings that we looked at the relationship between the number of bedrooms and the number of closets, we find a correlation between those 2 variables of 0.8. Is that okay? What would happen if I swap these 2 numbers? So I say the place with 2 bedrooms, we had 4 closets, and the place with 3 bedrooms, we had 6 closets. What would happen to my correlation?
Very strong. Stronger.
Okay, my correlation, so these numbers would change, okay? So 2 minus 2.5 is negative 0.5, and 3 minus 2.5 is positive 0.5, and 4 minus 5 is negative 1, and 6 minus 5 is positive 1. And so when I multiply these out, here I would get positive 0.5, and here I would get also positive 0.5. The sum here would be 10. And when I calculate my correlation, I get an R value of positive 1. And my plot would look like that. Okay. So what we see is that when we are above the mean, so to have a correlation of positive 1, it means that when we are above the mean in X, we would expect to be above the mean in Y. And if that's the case, we contribute a positive amount towards this sum product. And when we are below the mean in X, we also expect to be below the mean for Y. And because we have a negative times a negative, we are still contributing a positive amount towards the sum product. In the other case, when we had the data points here and here, these 2 values were contributing a large positive amount to the sum product, but the 2 middle points were contributing a negative amount to the sum product. But the amount that's being contributed by these 2 points was less than the ones contributed by the other points. And so overall, the amount that we have was still positive, and so we still have an overall positive relationship. What would happen if, and we don't have to do this, but what if our 4 data points looked like this? What would my overall correlation be? In this case, if my 4 data points were here, 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 and here, my overall correlation would be 0. These 2 would contribute positive towards the sum product, so these 2 would contribute negative towards the sum product. And we can see kind of the magnitude of these 2 is equal to the magnitude of these 2, and so overall everything would cancel out, and we would have a correlation of 0. So when we're talking about correlation, we want to kind of think of how much is this contributing towards the positive and the negative in terms of, are we above the mean for x and above the mean for y? Is that okay? All right. So on the final exam, I think it's reasonable for me to give you a small set of data points, maybe 4 or 5 data points, and ask you to calculate the correlation of a set of 4 or 5 data points. Okay. The truth is if you have any more data points than that, okay, if you have like 50 data points, you don't want to be calculating correlation by hand. Okay, it's large chance of making a mistake, and it's just much faster and easier to throw them all into the computer and ask the computer to calculate correlation. Okay. So, truth be told, rarely does anybody calculate correlation by hand. But I think there's some merit in learning how correlation is calculated and seeing how we have positive or negative values in the sum product when we see that. Okay. Okay, so you can calculate correlation, and whether or not you use the computer or you calculate correlation by hand, we also have a test to see if correlation is significant. The observed correlation statistically significant. So just like everything else we've learned in this class, we asked, is what we see here, is this statistically significant? Okay? And so when it comes to correlation, we can do a hypothesis test. The null hypothesis is that there is no correlation between the variables in the population. And so, symbolically, we write the null hypothesis is that rho equals 0. This is not a p, it's a is rho. So we use Latin letters, the R that you are familiar with for statistics, and we use Greek letters for parameters in the population. So rho is the correlation that exists in the population. So if we think of our bedroom and closet example, okay, well, we had 4 data points. And R was equal to 0.8. Okay. And we were looking at bedrooms and closets, right? So our null hypothesis is that the number of bedrooms and the number of closets in a place have no connection, okay? If I tell you there's this many bedrooms in a place, you have no idea whether the place is going to have a ton of closets or very few closets, okay? That's what the null hypothesis states, okay? If we see 4 places, and we've got a correlation of 0.8, is that an indication that there is a significant correlation in the population? That's what we want to know. What do you think? Maybe, maybe not. Okay, we only looked at 4 places, so it's hard to say, can we jump to any kind of conclusion based on 4 places alone? Maybe we can, maybe we can't, okay? The alternative, so the null is that there is no correlation. The alternative is that there is a correlation. There is correlation in the population between X and Y. Okay? And like anything else, it could be not equal to 0, or correlation, you could have a directional test, correlation is positive, or you can have a directional test where correlation is negative. Okay? Alright, so to do this test, believe it or not, we just have, we're just going to jump to the test statistic that we're going to use. The test statistic actually follows a t-distribution. Is n minus 2 over 1 minus r squared. Okay? Square root times r. This is our test statistic. Notice that we have n minus 2 in the numerator, which means if we're testing if correlation is significant, we need to have more than 2 data points. Okay? And that makes sense, because if we only had 2 data points, they will always be in a straight line. Okay? They'll always look like they're in a straight line. Okay? So the question is, if we have more data points, does it indicate that there's significant correlation in the population? Okay? So we'll go ahead and calculate this for our data set. We had a correlation of 0.8 and 4 data points. So what do I get here? I'm getting a test statistic of 1.886. The degrees of freedom is n minus 2. Again, indicating that we need more than 2 data points. And so I go to the t-table of 2 degrees of freedom and I look up 1.886, and coincidentally enough, that is an exact critical value that we get. Okay, and so with degrees of freedom equal to 2, and a critical value of 1.886, we get our tail area is exactly 0.10. Okay, this doesn't happen very often. But sometimes you get the, in the table we see that with 2 degrees of freedom, it says 1.886 corresponds to a tail area of 0.10. Okay, so that's kind of neat. All right, I have if I'm going with a non-directional test, that p is not equal to 0, then I would double my tail area. Okay. Or I guess we could go with a positive correlation. I don't know. Should we have done a directional or non-directional test? No. Let's just say we were going with a non-directional test. Then my p-value would be double this, and I would have a p-value of 20%. Alright, so what does it mean to get a p-value of 20% in the context of this problem? So the p-value is the probability of observing data like ours, or something more extreme, if the null hypothesis were true. Alright, so my p-value is 20%, okay? So what this says is that if the null hypothesis were true, if there was truly no relationship between the number of bedrooms in a place and the number of closets it has, the probability that 4 randomly selected points has a correlation of 0.8, that, or greater, that probability happens about 20% of the time. Okay? Or another way to think of this is that if you blindfolded someone and had them throw darts at a board, okay, and where the darts end up, we're just assuming is going to be a random place somewhere on the board. Maybe that's not accurate to say about dart throwing, but let's just say we're throwing 4 random darts at the board. What's the probability that the 4 darts end up forming a correlation of 0.8? Okay. It happens about 20% of the time. Okay. If we're just picking 4 random points, we're going to get a correlation of 0.8 about 20% of the time, just from random chance alone. Okay. So this p-value, the interpretation is, so even if there is no correlation, between x and y, for randomly selected points, will produce a correlation of 0.8 or more. And because we did a non-directional test, it also means negative 0.8 or more negative. Okay? 0.8 or more and negative 0.8 and more negative produce a correlation of 0.8 or more 20% of the time by random chance alone. So in this case, we would not have enough evidence to conclude that there's a relationship between the number of bedrooms and the number of closets in a place. Probably if we collected more data, more than 4 locations, we'll definitely see a correlation between the number of bedrooms and the number of closets. But with just 4 dwellings and correlation of 0.8, that's not enough to convince us that correlation exists in the population. Yes?
For the degrees of freedom, what's the reasoning behind subtracting 2 instead of 1?
And because if you only have 2 data points, they'll always form a line. Okay.
Okay.
So we'll need at least 3 data points to test if they are in a line. Let's see. We are burning up our time. I'm going to just keep going. All right, so let's talk about linear regression. Linear regression, we're dealing with trying to fit the best line to our data. Okay? This linear regression is finding the best fitting line. So let's just continue dealing with our bedroom closets example. It's just us. What is the line that's going to fit our data best? Is this the best fitting line? Or is the best fitting line something else? What is the line that best fits our data? Okay. Well, when we're talking about linear regression, a lot of times we're talking about what we call least squares regression. And the way we define the best line here is we say the best line is the line that has the smallest squares of residuals. Erase this. Okay, so let's say I picked the line y equals 2x. Is this a good line? That's what we want to know, okay? Well, we are going to evaluate how good or bad this line is by calculating the sum of squares residuals. Okay? So what is a residual? A residual is the difference between the actual data point and the predicted data point. Okay. And we're going to evaluate how how good this line, how well this line fits the data by looking at the squares of residuals. Okay, so according to this, okay, if I have x is equal to 1, and this is the line I'm using, what would I predict a place with 1 bedroom would have? How many closets would we predict? 2. We would predict 2. And if a place has 2 bedrooms, we would predict it has 4 closets. And if we predict a place has 3 bedrooms, we would predict it has 6. And 4, we would predict it has 8. Okay? And so, the residual we can think of as the vertical distance from the line. Okay? So, at a place that has 2 bedrooms, we are predicting that it would have 4 closets, but in actuality, the place we looked at had 6 closets. For a place that has 3 bedrooms, we are predicting that it would have 6 closets, but in actuality, when we looked at the place, it had 4 closets. Okay? But for these 2 places, what we predicted was what we found. Okay? So we have no residual here. So if the data point is on the line, there's no residual. And if the data point is off the line, the vertical distance to the line is our residual. Okay? I should have created, if you have room in your notes, put the residual column to the right of that. But I'm going to just put the residual column here. And so our residual here would be 0. And I would have a residual of actual minus predicted positive 2, a residual of negative 2, and a residual of 0 there. And then residual squared, I would have 0, 4, 4, and 0. So I can illustrate this by drawing squared residuals. Is that okay? Yes?
Sorry, how did you get the predicted again?
The predicted, I'm just plugging in my x. So if this is my, if I'm asking, is this a good line? I would plug my x in here, and I would, oh, I'm sorry, I need to put a hat there to indicate that it's a prediction. Okay. So what we're predicting is what I'm getting over here. According to the line, I'm predicting this, okay? So for this line, our sum of squares residuals is equal to 8. I'm just adding up my column of squared residuals. Alright, so let's try another line, and for the same data set, and I'll draw my it's our data set x, y, 1, 2, 3, 4, and I have 2, 6, 4, 8. Okay, we're going to try another best fit line, and it's going to be y is equal to 1 plus 1.6 x. Okay, so this is another line, and we're going to see this is y equals 1 plus 1.6x, and it looks kind of like that. And so here we see we've got a bunch of residuals, okay, I mean, we have residuals at every data point, And we're going to find the total squared residuals, okay? So our prediction according to this line, and we'll look at the residual and the squared residuals, okay? So according to this, if I have one bedroom, I would predict that I have 2.6 closets. And I know that sounds silly, but it's okay. These are just predictions. Of course, we're not going to have exactly 2.6 closets. We're either going to have 2 or 3 closets. But according to our best fit line, we're predicting 2.6. And just continuing to plug these in, I get 4.2, 5.8, and I'm having trouble here, 7.4.